Okay, so today I want to start the next chapter. It's called integrals, but of course for learning integrals, we need to know the notion of a primitive function, or you might call it an original function. What do I mean by original function? So you differentiate a function, you get another function. Primitive functions, they want to go in the other direction. So that's as simple as that, yes? So that's the meaning of a primitive function. So let me start officially. What is the primitive function? Okay, so a function, and this is more or less a standard. A function, write it capital F. A function capital F is said to be a primitive function of the function f if f prime is equal to f. So write the first one with capital F, the other one with lowercase letter f. So we say that a function capital F is said to be a primitive function, and let me emphasize here, a primitive function of the function f if the derivative of the capital F is equal to the little f, as simple as that, yes? So for example, functions I don't know, let me write f1 of x equals to x squared plus 5, and f2 of x equals to x squared plus 3 are both primitive functions for the function f of x equals to 2x. Okay, since, why is that? Because if I differentiate this function, it is 2x. If I differentiate this function, that's also 2x. So as simple as that, yes? So f1 prime of x is equal to x squared plus 5 derivative, and this, you know that it is 2x, and this is just little f of x. And the same is true for f prime 2 of x. It is x squared plus 3 prime, and that is also 2x, and that is f of x. Yes? Is that clear? So first of all, can you guess another primitive function for the same function for me? Yes?
x2 plus 1.
Plus 1. Okay. So probably the simplest primitive function, if we know what's the meaning of simplest. So what's the simplest primitive function for like 2x? x2, yeah, probably x2 is the simplest one, yes, without any constants at all. But then it becomes very clear that if I have one primitive function, any primitive function, if I add any constant to that primitive function, it becomes again another primitive function. Is that clear? So if x squared is a primitive function for this, which it is, because if I take the derivative of that, it becomes 2x. If I add any constant to this, any constant that I like, I generate a new function. This function is different from that function, but still its derivative is the same function, yes? So this one, that one, this one, all of them are primitive functions for this one. So this is more or less trivial. If I have a function whose derivative is this, if I add any constant to that, it becomes that one. But the other way around is also true, but it is above the knowledge of math at the high school to be able to prove it. Okay, so let me write a remark here for you. Okay, let me first explain it. So let f be a primitive function for f. translate this sentence into mathematical sentence, into mathematical symbols. When I say capital F is a primitive function for f, what do you understand from this sentence? What do you understand? Yes?
That capital F prime is
Yes.
equal to F.
Okay, so this is the mathematical way of expressing the same fact. The capital F is a primitive function of f. Now, the claim is that if I add any constant to c, any constant c to the function f, this is still a primitive function for the same function. Yes? Because if I differentiate this, you know, it becomes a derivative of the first one, the derivative of the second one, but the derivative of the first one is little f, the derivative of the constant is 0, so you get the same function f back. Okay? So this direction is trivial. The other direction is not trivial, but I want you to know that is also true. What does it mean? It means that if you have two functions, f1 and f2, whose derivatives are the same function, then you can conclude from this that the difference between these two cannot be that much. They at most differ by a constant. This is not trivial. This is different from here. Okay? So if I have two functions whose derivatives are the same function, they cannot be totally different functions. They are either exactly equal or they can at most differ by one constant, that is. So it means that if you see something like this, you are allowed to conclude that the difference between these two is a constant. Okay, not more than that. This constant, it might be 0, then they are exactly equal, but this is not the case. For example, it cannot happen like this. f1 of x minus f2 of x. If you see someone has written this, this is definitely wrong. Because you are saying that these two functions are primitive functions of this, and now you are saying to me that the difference between functions f1 and f2 is x. This x is not a constant. So this is definitely wrong. You cannot find, this is not trivial, but you need to trust me on that this is actually a theorem in mathematics. Is that understandable? So this one is exactly very simple. At the level of your lesson, you can see the proof. If f is a primitive function of f, if I add any constant to it, it is still a primitive function. But the other one is also true, but I want you to know about that, but don't worry about the proof for the time being. If I have two functions whose derivative is equal to the same function, the difference between these two functions should be a constant, not more. Okay? Okay, so let me now write this remark here, and then we continue. Okay, so the remark is this. If f is a primitive function of f, then f plus c for any constant c is also a primitive function for little f. So the proof is easy, as I explained. Actually, I explained the proof for you. But the other way around, if f1 and f2 are primitive functions for the same function, F, then one of them, one of them, you can say it doesn't matter. Some books write it in the way that I saw. Some write like this. They say that the first one is the second one plus a constant. Then, or the difference between them is a constant. It doesn't matter. Then F1 is equal to F2 plus C for not any, but for some constant C.
Which constant C does not work?
No, what do you mean?
Is that for some constant C?
No, because we don't know. If I want to see for which, what is this constant, I need to know the functions. If I don't know the function, even if I don't know the functions, but still I can say something. I can say the difference is a constant. Which constant depends to the behavior of these functions, of course. Yes? So, what does this mean? This means that from now on, you can concentrate on finding only one primitive function. You are relieved now because you don't need to be worried about if you are losing an opportunity to find another primitive function. This guarantees that, don't worry. If you just find one of them, other ones are the same plus some constant. Okay, this is important because you saw that I gave you three functions. They were the primitive function for the same function. You might, in principle, think, is there any odd, very complicated odd function in this universe that we differentiate that function, then there are a lot of terms, but they cancel out, and at the end, it remains 2x? This theorem guarantees, no, don't worry. This is important to understand. Don't underestimate this theorem, okay? So let me just repeat this because it is important. So I just gave you 3 examples. Do you remember? It was x to the 2 plus 5, x to the 2 plus 3, and x to the 2. The derivative of all of them was just 2x. Okay, this is easy to understand. But in principle, I want you to appreciate this question. You might ask yourself, it might be possible there is a function which we don't know. It might be very complicated, but when I differentiate it, it produces a lot of terms. Some positive, some negative, they will cancel out, and what remains at the end is 2x. This theorem tells you that don't worry, you cannot find that. Any function whose derivative is 2x is simply x squared plus a constant. Is that understandable? So, okay. So this is very, very crucial to this. So this is why from now on, if you look at the book, there is always a constant in the book, and this is the case. If I ask you find a primitive function for 2x, a primitive function, all primitive functions, the primitive function. So this is very important. In Swedish, there are probably corresponding words that they can ask you, okay? So a primitive function, if I ask you find a primitive function of 2x, if you write for me x plus 5, you get the full mark. If you write x squared plus 3, you get the full mark. If you say x squared, you get the full mark. But which one do you prefer? If I ask you a, probably the simplest one. So this is why when I ask you a, you don't see some constants there, not because there is no constant. People have chosen that constant equal to 0, because it is the simplest possible choice. And if we say all, okay, all primitive functions, how should you answer this question when I say all? For a, 2x is good enough. Each one of them is enough, but I prefer to write I prefer to write x squared. But if I write all, what do you think I should write?
X squared plus C.
Plus C, because of that theorem. Because when you find one of them, by that theorem, it is guaranteed all of them are the same, they differ at most by an additive constant, not more. So when you say all, you have to show me that you respect this word and write C, okay? And when I say there, it would be the topic of the next lesson. or probably if we can cover it today. When I say there, it means that I have to provide you with an extra piece of information so that you can use that piece of information to find that particular value of C. Then it becomes the primitive function. It means that that unique one, which is not only the primitive function for my function, but also fulfill or satisfies another condition. So please appreciate these words when you are dealing with primitive functions. Okay, so is that understandable? Yes, is that clear? Okay, now for the time being, you might say, what is the problem? Why we should find primitive functions? At least when I wanted to talk about derivatives, I don't know if you remember or not, I actually gave you two problems to motivate you why we need to look at derivatives. Yes? What was that? Do you remember? There were two big scientists who were working on this, one from mathematical curiosity point of view and one from physics point of view. Do you remember? That was the motivation. Why? At least I gave you two motivations. Of course, then I gave you, I don't know, Maxwell's equations. There were a lot of derivatives there, and then technology highly depends on Maxwell's equations, and etc. and etc. But right now, I cannot motivate you why primitive functions is good, but you need to wait to see what happens. Okay? In the next lessons, I will motivate you. For the time being, primitive functions, you just look at it as a game. Just a mathematical curiosity. You want to think, okay, can I reverse the operation? You told me I differentiate a function, get another function. Now I want to think that, can I go back and find the primitive original function or not? But definitely, the reason that we will be interested in this comes from Newton's theorem again. Okay, so we will talk about this a lot. Okay, but do you remember, because nobody talked, do you remember what was the motivation behind derivative? How is that possible? The motivation behind derivative was the slope of the tangent line from the mathematical point of view and finding the instantaneous velocity of a moving particle. No clue? Yes, please work on your memory a little bit. This is very important. Okay. So these, by the way, these are very important. What I'm saying is that real mathematics is something you know how to differentiate. This becomes probably worthless if you don't understand why we differentiate.
I thought you meant a particular exercise.
No. In general. So the broad, yeah, I know. I knew that you know. Probably you don't appreciate the question. This is what I'm saying. The reason people started learning about derivative because these two guys, Leibniz and Newton, were asking questions. How can I calculate these things? And calculating those things, the slope of the tangent line and instantaneous velocity of a moving particle, gave rise to the definition of a limit. And if you remember, and I told you that the limit becomes important when it appears in two different perspectives. So people become interested and try to investigate the properties of them. Okay, so now for the time being, for some lessons, try to think it in this way. This is just like a game. Okay, I am asking you, can you give me a function? Derivative is the function that I am telling you. Okay, for the time being, you consider this one like that. But definitely, I will motivate you why this becomes important. Okay, and it might be you don't believe it or believe it. It relates to the area. If you want to calculate the area, for example, we know how to calculate area of polygons, yes, because we partition them to triangles and then of course from ancient times we know about circles and things like that. But even for the circles, why the formula is pi r squared? I don't know. Have you seen this proof before? There is a question why the area of the circle should be this one. There are two different perspectives for the circle, of course. But if I have this situation, if I have a curve, just an arbitrary curve, and then I want to find this area. Okay, so this, you will see that this primitive function is related to calculating these areas, which is not directly clear. And that was the genius of Newton, actually, who discovered more or less something like that. Okay, now let us go and start. Okay, now we want to start a new game. Finding the primitive functions. Okay, any Any questions so far? Is that understandable? Okay, so now I want to start the new game. Where should I start? Where did I start when I wanted to start the derivative game? So these are important questions. Of course, I can give you the instructions.
You started to categorize it.
Exactly. That's a very natural. You don't even need memory. It's natural. Just think about it. I want to find a game. I want to set up a rule for my game. So what should I do? There are a lot of functions in this world. Okay. So I need to categorize them. Okay. And then the simplest one is again this one. Okay. So most of this work that I am doing is based on educated guess. But then you might say that, okay, what is the benefit of guessing if I want to guess every case? But this is not the case. It will give you calculational abilities. Okay, so what I do this time, I put small f here. Do you remember in the derivative table, I put f prime there. But now, what should I put here? Can you tell me? Capital F, yes? I want to write the capital F there. Okay, so what is the simplest possible function that you can imagine?
Constant.
A constant function. So let me just try. If I ask you, can you give me a function whose derivative is 1?
X.
X, yes? A function whose derivative is 2?
2x.
2x. A function whose derivative is 3? 3x. Okay, a function whose derivative is 0?
C.
A constant, yes? Do you agree? But is this the only function whose derivative is 1? We just learned no. How many functions are there whose derivative is 1? Infinitely many, yes? 1 for each constant. 1 for each constant. 1 for each constant, yes? And then now I'm asking you, if this is 1, it is x. If this is 2, it is 2x, 3x. So if I have in general k, what's that? K is a constant. What is that? Kx, yes, the derivative of kx is k. And then I have to add a constant c at the end. Is that understandable? So you see, that's completely a guesswork. Is that understandable? Okay. So now let me test your understanding. Oops. So this is k is a constant. Constant. Okay, now let me ask you, f of x equals to square root of 2. Can you tell me what is the capital F? So let me write all primitive functions. Okay, tell me, what is this? Yes, square root of 2x plus c. Agree? This is a primitive. So I want you to ask, if someone asks you what you are doing, you are telling that person that I am finding a primitive function. What does it mean? It means that I am finding all functions whose derivative is equal to that. Is that understandable? Understandable or not?
Yes.
Okay. Now let me give you another function. What do you think about this? Yes? And let me give you this. What's the primitive function for this? Y times x, yes? So that's what I'm saying. You don't need to be worried. As far as you have something which is constant, again, you have some smile on your faces because you think that these are trivial, but I have seen people make mistakes, yes? So, yeah, trust me. So this is this function, yes? And now let me ask you, what about this one? Do you think f of x is equal to pi? Pi x. Pi is a constant. So it is a fancy way of writing constants. All of them are, yes, what about this one? ln of 2 over 3. 2 over 3 times x, yes? Because these are constants. All of them are constants, yes? So it means that primitive function for this is ln of 2 over 3 times x plus c. So you don't need to be worried about the constant. What about this one? F of x equals to pi squared plus Euler number, I don't know, to power 2 plus ln of 3. What is a primitive function for this? This is again a constant. Who cares what is, because pi is a constant, pi to the power 2 is a constant. It's a fancy constant, but who cares? This is a constant, so its primitive function again is the whole thing, yes, multiplied by x plus c. And if I ask you a primitive function, what you do, the only difference is that you can choose whatever you like for c, but probably people choose c equal to 0 because this is the simplest choice. Is that understandable? And we haven't talked about the primitive functions yet. We will come back to it. So finished. This is the constant function. We are happy. And now we go to the next function. Let us discover that rule. Let me clean this part. So let us discover this rule now. What is the simplest possible function after constant functions? All these words are ambiguous, but probably because we are humans, not robots, we understand what I mean, yes? What is the simplest possible function after constant functions? X. Yeah, why not x? This is the simplest possible function. Now I am asking you, can you guess a function whose derivative is x? You find some connection between a function whose derivative is x. What should be that function look like? Yes, x squared at least. Because that's a good candidate, yes? Because if I differentiate x squared, it becomes 2x. But this is a little bit annoying because when I differentiate this, it will bring down a 2 for me. But if I look ahead, what is happening, I can compensate for that 2 which is coming down by dividing by 2 from the beginning, yes? Is that understandable? Because I put this 1 over 2 here. If I differentiate this, then this 2 that is coming down because of differentiation rules will be canceling this one. And then it becomes x, and that would be my function. But do you think that there is another very complicated function whose derivative is equal to that? No, because of that theorem, which was a little bit higher than the level of this course. So this guarantees that don't worry. This is the only function whose derivative is this. Other functions might at most differ by a constant. Is that understandable? Yes or no?
Yes.
Okay. Now let us just try to do this analogy. So what happened? Can you guess a function whose derivative is x squared now? So you know there is a relation. What type of function should this be? It should be related to x to the 3, yes? Because if you differentiate, 3 goes down and it gives you x squared. But unfortunately, there is no 3 here. So you need to look ahead of you. So what can you do?
You divide by 3.
You divide by 3, yes? And you divide by 3, and that is the c constant. So do you agree now, if I differentiate this function, it becomes that? Is that understandable? Yes? Okay, now if I want to draw, if I continue this pattern, so what happens if I have this situation in general?
1 over a times x to the power of a.
Do you agree? Because here, when the power was 1, you have one more, add 1 to it, it is 2 and 2 here. When it is 2, it is 3 and 3 there. And when you have a, apparently you can guess. It is 1 over what? A plus 1, x to power a plus 1. And then, of course, if you want, you can add a constant to it. Okay, but this is a guess. If I ask you to prove it, how do you prove your guess? If I want you to prove it, you need to patiently differentiate this very rigorously and show that the derivative is this one. So let us do that. The way that I did it, I want you to come up with a pattern. But when you have the pattern, you should show the pattern is working. Yes? So how should I show the pattern is working? I differentiate this. Okay. Do you remember? This is a constant. Okay? And then it means that I write it here. But if I want to differentiate this, a plus 1 goes down, and then x to the power of a plus 1 minus 1. Differentiation rules. Yes? And the derivative of the constant is 0. This a plus 1, which is coming down, will be cancelled by this one, and a plus 1 minus 1 is just what? A. And that is exactly your function. So your guess was indeed correct. But apparently this guess does not work for one particular case. And you need to wait until Math 4, unfortunately, to learn that particular case. Can you tell me which particular case? -1. Because if a is -1, then I will have problem here. The derivative becomes 0. Yes? So it means that what happens if I have x to the power of -1? What is the function whose derivative is this? You will learn in Math 4 that is ln of x. So it means that it changes dramatically. Yes. So far, the functions are polynomials, but suddenly when it comes to this particular case, it becomes a logarithmic function. Okay. But you need to wait. Don't worry about that. So whatever is happening here, I will give you the cases that a is not equal to minus. Okay. Okay. So now I add the formula, and I am a little bit more happy, yes, because now I have 2 formulas. If you have 3, you will be very happy, yes. We will have 3, I think, in Math 3C, yes, 1 exponential functions, yes. Okay, let me just, I want to solve a lot of examples using this. Might be this is very boring. If this is going to be the case, okay, what is the boring lesson is that? But it is not. By the way, I love finding primitive functions. This is one of them. When I feel depressed, I start finding primitive functions. It really helps. Yeah, you need to find something to enjoy. Okay, this is one of those topics. Combinatorics is also very, very fun for me. Okay, so let us write this formula here for you. X to the a, and please try to use memory. Memorize them. Okay. So this becomes 1 over a plus 1, x to the power of a plus 1 plus c. So this is another formula in my toolbox, and I emphasize here that this shouldn't be the case. But I need 2 generic rules that doesn't depend on any function, and I don't know why the book hasn't talked about that. The first bad point is that primitive functions in any other books is denoted by this symbol. There are no symbols in the book for primitive functions. Okay, so I don't know, should I? Let me not use it. I want to invent my own symbol, primitive, yes? It's a very smart way of, yes, that's primitive function. And then I want to teach you something. This is very strange in the book, they haven't talked about. Do you remember I talked about the sum rule? This was not mentioned in the book, even though all the time we are using it, yes? So this was f prime plus what? G prime, we called it the sum rule or the difference rule. And there was one more rule on except this. Do you remember? The sum of 2 functions derivative, the difference of 2 functions derivative, and C times f derivative. Constant times derivative. It is CF prime. Do you agree? Okay, now we have similar things for primitive functions, but because your book isn't using this for some good reasons, so let me just invent momentarily something like this by PRM, I mean primitive function. And now I want to ask you the same question. What do you think the primitive function of the sum, how this primitive function will be related to the primitive of these functions individually? This is also needed. You see, I am not talking about a particular function. This could be quite very, very complicated functions, even if you don't know how to find the primitive function. It doesn't relate to them. I am asking you, I have given you 2 functions, and I add them, and I want to ask you, what is the primitive function of this sum? Or I am asking you this, is there any relation between the primitive of a sum with the primitive of each one of these functions? So for the derivative, we learned that the derivative of the sum is the derivative of the first one plus the derivative of the second one. In other words, do you think that is still true, that primitive function of this one is the primitive function for the first one plus the primitive function for the second one? Do you think that this is true? Or in other words, this one is true or not. Primitive function for a constant c times f. Do you think I can pull this c out and just concentrate on finding primitive function for f? Okay, so I want to discuss about these two, and then we start solving problems, which are nice. So the rules, I don't know, for some reason they are not given in the book directly, but the book is always using them. So they are true, actually. Of course, there is a little bit of ambiguity because of that constant, but assume that I am considering all primitive functions here. So let us check this question mark is true. Okay, I want to show that this question mark is indeed a true equality. How should I show that? I would say that let primitive function of f, let me call it capital F. This is the standard way of writing. And let me say primitive function for g is capital G. So I am naming the primitive function of little f to be capital F as a standard way of denoting them, and the primitive function of g to be capital G. Okay, can you tell me what can I conclude from this statement immediately? So what can I conclude? What is the meaning? What is the meaning of primitive function of f is capital F? Just come on. What is the meaning? I told you, you should be able to translate this sentence into mathematical symbols. Capital F is the primitive function of f. What you can write below this? Write something at least. Otherwise, I will shoot you.
Capital F prime is equal.
So it works, yes? Yeah. It's actually a very nice way of teaching, yes? Okay, so f prime of f is equal to f. Is that understandable? And now what about this one?
Capital G prime is equal to.
Okay, I was using my gun actually. Okay, so this is actually this. Is that understandable? So, and now let me ask you something. Do you agree with this, that I can come and conclude f prime plus g prime, f prime plus g prime? Do you agree with this one or you don't? Yes, I agree with this one. So I myself named this one with capital F, named this one with capital G. These are the consequences of definition, nothing else. And this is a logical consequence. If an expression is equal to another one, this one is equal to what? This one, I can add them side by side, but still they are equal. Yes? And now, what do you think about this? Do you agree with this one? Instead of writing f prime plus g prime separately, am I allowed to write f plus g prime? Yes, because of the lessons that we learned in derivative. Okay. Now, can you translate this in the using the primitive function? What is the meaning of this? You have a box whose derivative is this one. What is this one with respect to this? Yeah, the box is a primitive function of triangle. Do you agree? That's the meaning. Now, this is playing the role of your box. This is playing the role of your triangle. So the box prime is triangle. So it means box is the primitive function for the triangle. So it means f plus g is the primitive function for the triangle. Do you agree with me or not? Yes? Okay, but now, what was f? F was primitive function for f, yes? And what was g? Primitive function for g. Addition. So primitive of f plus primitive of g is equal to primitive of f plus g. Okay? So from now on, you have this rule. Primitive of the sum of two functions is the primitive of the first one plus the primitive of the second one, even if the function is so complicated that you don't know the primitive functions. Okay? But this rule is there for you. And the same thing, I don't want to prove it. You can prove it as an exercise for yourself. If there's a difference, there is also true, and this one is also true. So this I don't know. You write it somewhere or learn it, because they are not either in the formula sheet, they are not also in the book, but you need to know. Okay? Now, these two rules are completely generic, but this table that we started this year, we will complete it next year, and you will still complete it more in the university. So this table is coming for you, okay? Okay, so if you want to work with mathematics, you cannot get rid of that table. Okay, so just get used to it. Yeah. Oops, I cleaned that. Do you want to write? Okay. But you can see the video later, probably. Okay, now let me start solving some problems, because every one of you, more or less, were able to guess this. But let me now give you another function. Of course, I want to increase the level of difficulty little by little. But you will see at the end, there are some functions that we cannot guess the primitive function for them. But using this table and these two rules, we can calculate them. And that is the power of mathematics. Otherwise, just guessing is worthless, yes? Okay, so this example is very, very important. So I want you to learn this example. I start with very, very simple ones, but I will increase the difficulty at the level of your lesson, okay? Determine let me start. Do you like to write all or a? Which one do you prefer? Determine all primitive functions or a? A is good, yes? I don't like C. Determine a primitive function for the following functions. But you know that that's not a very big restriction, yes? If I write all, you have to write C. Function for the following functions. Okay, so I want to keep these formulas. So let me write the formulas here for you simpler, so smaller. So I have k, it becomes kx plus c, and then I have x to power a, it becomes 1 over a plus 1, x to power a plus 1 plus c, and here I emphasize that this shouldn't be -1, and I can clean all of these, make them smaller, so that we can have more space to write these things down, okay? And then we learn that primitive function of f plus or minus g is equal to the primitive function of f plus or minus primitive function of g, and then primitive function of a constant times f is equal to c primitive function of g. But let me emphasize that I have seen some mistakes. Don't think that the primitive of the product is equal to the primitive of the first one multiplied by the primitive of the g. Please write it down and cross it over to emphasize that this is not correct. For division, it's not correct either. So okay, so please make sure that these are not correct ones. Okay, so let us start with very simple ones. So f of x is equal to (5x to the power of 3). I want to start with very, very simple ones. I want to find a primitive function for this simple function, but I don't want you to every time guess. You need to learn how to use these tables and these two rules. So here, one rule is needed because I have a constant multiplied by a function. And I am interested in finding a primitive function for this combination. So the first rule before seeing the table is this rule, that I have a constant. So I put the constant there. I just write f of x is equal. I put the constant here. And I concentrate, oops, sorry, why I have written g, this is f. So I have I put the constant here and I concentrate on finding the primitive function or a primitive function for the function part. What is the function part? The function part is x to the 3. And x to the 3, is it in my table somehow or not? It is this formula. Okay, so this formula is given to you in the formula sheet. So you need to use these two rules and the formulas in the table to be able to find the primitive function. Okay, so I put 5 here. Now, can you tell me what is a primitive function for x to the 3? Let me be patient and write everything. This a is now 3. So it becomes 1 over a plus 1. Look at the formula. And x to the power of 3 plus 1. And because I have emphasized here a primitive function, I don't need to write c. Is that understandable? And now you simplify it, because 1 over 3 plus 1 is 1 over 4, and then you multiply it by 5. So I will have 5 over 4, x to the power of 4. So that is a primitive function. If you don't believe, let me ask you, what is the meaning of this function? Can someone tell me what is this function? Yes?
The derivative of that.
Is this, okay? And we didn't guess, okay? But it might be not very hard for you to guess even for this case, but I will give you harder examples that I would say it's very hard to guess. Is everything clear here? Now let me just ask you this. A little bit harder one, more terms. For example, I have 3x to the power of 2 plus 2x minus 1. I want to find a primitive function for this. Okay, let us see. What are the rules? Can you tell me, do I need, which rules I need, which formulas I need? Do I need this rule? Do I need this rule? Do I need this formula? Do I need this formula? Yes?
You need everyone, all of them except the multiplication one.
Multiplication one is wrong.
No, I mean the constant before the function.
This one?
You don't need that one, but everyone else.
This one you also need. Yeah.
Oh,
everything you need.
Okay, then you need everything.
Everything, yes. Because, first of all, why I need this rule? I need this rule because I have the sum and difference of functions. Yes, the sum and difference of functions. So I need this rule. This rule tells me, don't worry, think about them separately. This is the meaning of this formula. I need this formula because in two of them, a constant is multiplied by your function. And this tells me, don't worry about the constant, just concentrate on the function parts. Okay? And then these two rules are needed. Is this formula needed? K1. Do you think this formula is needed for this one? Is this formula needed?
Yes.
Yes. For which part?
3x.
No, not for 3x.
Oh, minus 1, minus 1.
Minus 1 for the last one, because this is a constant one. Yes. Is this formula needed? Yes, because of two parts. 1x squared, 1x. Is that understandable? So this is, you need to increase this skill. That's it. So you need to know which rules that you are using. And it is very, very simple. Okay? So I would immediately write that capital F of x is equal to. Tell me, what should I do? I need only concentrate here, and I don't need to be worried about this multiplicative constant. I just write it there, and I concentrate on finding a formula in my table which suits this one. Okay, what is that one? It's clear. This is this formula. So let me be more a little bit patient these days for the first exercises. So I would write 2 plus 1, x to the power of 2 plus 1. But yeah, I would say that you have to do it in your head. Everything, if you want to write it, would be a mess. Okay, now let us go to the next step. What happens here? 2 is a constant, so I just write it down. What is playing the role of a in this term? 1. A is 1 in this term, yes? Because the power is 1. So what I write is 1 over 1 plus 1, x to power 1 plus 1. And then what is a primitive function? You see, I have negative. I put negative because of this rule. And now I concentrate on finding a primitive function for 1. Don't say that this is this rule. There is no rule here. This is this formula. That's a constant number. What is its derivative? What is its primitive function according to this rule? 1 times x, which is x. So it becomes minus x. Okay? Is that understandable? And now you simplify that. And let us do simplification in our head. What happens here? Can you tell me? It becomes 1. Yes? And so it becomes x to the 3. What happens here? 1. It becomes x to the 2 minus x. This is your function. And you can immediately confirm. Take the derivative of that, it becomes this. Is that understandable? So these are simple things. But sometimes you cannot start primitive functions immediately. You have to change the form of the function so that it suits to one of these. It matches with one of these formulas that you have. So you need to learn this one. These are E-level problems. They are very simple. Okay, now let me go to a little bit better problems. So the first thing is what I can do if I write this one for you. So I would say this, the third root of x. Yes. I want to find a primitive function for this. So what should I do?
X to the power 1 over 3.
Yes. So remember, if you have forgotten, let me write this one here. So nth root of a is a to power 1 over n, and the nth root of a to power m is a to power m over n. Okay, so these formulas are very important. So you see that I cannot immediately start primitive function here because the third root of x is not in my table directly. So I have to change the form so that it matches with one of these formulas. Otherwise, you cannot do that. Okay, so what should I do here? The first step is still, you see, I am writing a small letter of f because I am not finding a primitive function. I am just changing the form of this function. So it becomes x to the power of 1 over 3. Can I use this formula for this case? Yes, because the only exception here is -1. But the power is positive 1 over 3, so that's safe. So what is the answer? Can you tell me? What should I write? I would write 1. A in this case is this number, so A is 1/3 plus 1. And then you have x to the power of 1/3 plus 1. Okay, can you do these calculations in your head? What's the answer to this?
3 over 4.
3 over 4. One way is to multiply the numerator and denominator by 3. So this becomes 3. If you multiply it by 3, it becomes 1, it becomes 3. So 1 plus 3 is 4, so it is 3 over 4. Yes? And what is the other one?
X to the power 4 over 3.
4 over 3. So that is a primitive function. Might be it was a little bit harder to guess immediately if I ask you what is a primitive function for this. And sometimes you might see this simplification, I don't care at this level, but you can simplify this a little bit. Can you go back to write it? So let me write with a different color. You don't have to, but I always care about beauty. I don't know. So let us follow it. So can I simplify? I really don't like these fractions. And actually, I hate fractions most of the time. So, but I hate decimals more, yes? Because of course here, this is decimal is good, 70. Yeah, that's correct. That's exact value. But most of the time, the fractions are better because exact values are closer to be more ideal, yes? So x to the power of 4 over 3. So what can I write that? The third root of what? X to the power of 4. Yes? But can I do better? Yes, because it becomes 3 over 4. X to the 4, what can I write x to the 4? I can write it as x to the 3 times x. Do you agree? But third root of x to the 3 is just x. I can pull it out. And then unfortunately, this poor x will be left in the prison, yes? And that is the case. So it becomes 3 over 4x times the square, third root of x. Okay, so what we can do for that? Yeah. So this is the better way of doing that. But when I write this blue, it means that this is, I'm not giving you, of course, it would be a credit for you. If I see these things, believe me, this will change my evaluation about you. But if you stop here, that's completely okay. You get the full mark there, okay? So this is one way to do this. Now let us go to more. I don't know. Could you come up with this answer for that? It is not hard. Do you agree? Was it possible for you to guess this function whose derivative is this one? If you don't believe, differentiate this. The function becomes that. Okay? It was not easy to guess, but we were not guessing. We were just following the rules. So it is working. It's not useless. Okay, and now let us go to another problem. Let us see what's your opinion about that. If I give you fractions, fractions is a very hard subject in it's not a very hard subject in differentiation. You will learn it next year. But when it comes to integration, it's very hard. So you need to wait until university to see that in general, if I have a fraction with polynomials and everything, how should I do that? Okay, so now let me give you another function, a simple one, but I want you to test your understanding first. So what was that number? Number 4. So let me write f of x equals to 1 over x to the power of 3. Let me start with simple ones first. This is a fraction, but not kind of fraction that we cannot do it. We can do it very easily. So I want to find a primitive function for this. By the way, is it easy to guess now? It's not that easy as before. Can you guess a function whose derivative is just simple function 1 over x to the 3? So I want to say that this is a little bit more than guessing. We are doing something here. We are not gathering in this situation to start guessing things, yes? So can you tell me how should I do that? The experience that you had from derivatives will help you here. Yes, Jonathan? Yes, that's as simple as that. So remember, it becomes x to the power of minus 3. Do I need this rule? No. Do I need this rule? No. Do I need this formula? No. Do I need this formula? Yes. So what is a here in this problem? Minus 3. Is minus 3 safe for this formula? Yes, because it's not minus 1. So I can use that. So what happens? The capital F. Just be patient a little bit. 1 over, this is your a, plus 1. Look here. A plus 1. And x to the power of minus 3 plus 1. Okay, what happens here? It's 1 over minus 2. 1 over minus 2, I don't know. It's ugly for me. So I write minus 1 over 2. And then x to the power of minus 2. You can stop here. But I would prefer to continue, yes? Because if you mess something up, it's better to fix it, yes? Because we started with positive powers. We messed it up with putting negative powers. So it is better to make it clean again. Okay, so that's my opinion. That's up to you. You can stop there. But let me write it with a different color. If you want to, you can continue. Can you tell me what is the answer to this? I don't know. Because you know beauty is a little bit subjective. But how do you see that this is beautiful? What is the most beautiful way of writing that, in your opinion? Yes?
Take it down and make it possible.
Yes, and then, okay, so which one do you prefer? This one? That's completely correct. You mean this one?
Yes, that's beautiful.
That's beautiful. Okay, from your perspective. But I will, yeah, I will prefer this one. I don't know. Yeah, this is more beautiful for me. The meaning of beautiful here means more simplicity. Yes, that's what. This is a more complicated object than that. Yes, because then I need to draw at this one. Then I need to take my pen, and I am very lazy, and then put it there. Yes. So from that perspective, from energy point of view, energy consuming point of view, I am using one more beam to do that. Yes. So yeah, this is exactly what it works. So if you want to consider, I'm using more energy to write that. If I want to do it in my head, I would prefer to write it in that way. Yeah, because I am saving a little bit of space. I don't know. That's up to you. Okay. Now let us go to a little bit harder problem. So what do you think about this? So I know that you have experience. If you have, remember actually what I was teaching you when derivative, the rules are the same or the ideas are the same. So now let me give you another function. So I will give it a little bit like this. So let me write 3x to the power of 5 plus 6x minus 2 divided by 5x to the power of 7. So I want to find a primitive function, and I hopefully you agree with me. It's not possible to guess. Do you want to guess it? give me a function whose derivative is this one. Yes. So you see, I am still emphasizing we are doing something. Okay. Okay. Tell me what is the starting point?
You separate them.
I separate them. So you see, that's the idea. Exactly, the idea is the same as differentiation. If I gave you this in the differentiation part and ask you to find the derivative, do you remember the rule? You need to separate them. Okay. Of course, this is not exactly the same problem, but the same idea still works. Okay. Do you want to do it yourself? Yes, just do it. Yes, just do it yourself. And remember that I have my gun with me. Yeah. Most of the technological advances is coming from this. We want to be secure. Yes, we want to survive. I can write you one more after you finish. Don't wait. So if you know these examples, you are on the safe side. So I think in the book, this one that I want to write more or less is a level 3 problem. So I don't know exactly, but I can just make something of that. Yeah, something like this. If you can do these two, don't worry at all. So you have learned everything. Do you think that you have these formulas in your memory? Yes. Let me clean them.
Is it square root of 2 or square root of x?
This one?
Yes.
This is, yeah, when I, square root of x. X. And you know that when I don't write something here, it means by convention it is 2.
Yes.
I actually don't know the English name for the number that we put here. So if you don't mind, let me start solving it because I want to finalize this lesson. We don't have that much time. So let me start from there. So at least you know the idea. The idea is to separate them, as you said. So I would write them separately. If you can do it in your head much better, of course, you need to be patient to make sure that you are not making any mistakes. So here, I will do this. And then you see that I have to simplify. So can you just tell me what should I write for this directly instead of doing it in 2 steps? So 3 over 5 is just 3 over 5. But what can I do with these x's?
X to the power minus 2.
Yeah, it is, of course, it is 1 over x to the power 2, but you know from previous experience that sooner or later you have to bring it up, and it is not hard to do that in one go, yes? So it is x to the power of minus 2. Just save some time, because if you want to write everything, this is, for myself, it's always the case. If I want to write too much, I make mistakes. Okay, so then x over x to the power of 7. What's the best way of writing it immediately?
X to the power minus 6.
Everyone agrees? Yes? X to the power of minus 6. And the other one?
Minus 7.
Minus 7. Now everything is according to our rules. Yes? So if I want to calculate this, so what I calculate, oh, sorry, it should be capital F. So it becomes 3 over 5, 1 over, at least you can do the addition in your head. 1 unit more. Minus 2 plus 1 is minus 1. Do you agree? And then instead of x to power minus 2, you have x to power minus 1. And then you have 6 over 5. Okay, 1 over what number here? Minus 6 plus 1, which is minus 5. And then x to the power, the same number, minus 5. Please let me know if you don't understand what's going on. And then here, minus 2 over 5 is a constant. What should I write here? 1 over?
Minus 6.
Minus 6, x to the power minus 6. And because it has been mentioned a primitive function, I don't need to write C. Otherwise, I have to write if it's all primitive functions. And then, of course, we don't leave this mess after us. We need to simplify this a little bit. So what's the answer? 1 over minus 1 and times this one. And then minus 5 times this is minus 25. And then minus positive. 2 and 6 are simplified. 3 multiplied here. If you stop here, that's okay. And I want to stop here because I don't have time to care for beauty now. But you can simplify. If you stop here, that's completely okay. And I hope that you agree with me. It was not easy at all to guess this function whose derivative is this function. Yes? But we were able to calculate. Any questions here? Okay, let me just do the other one. So number 6, yes. So what should I do first? I have to do a lot of things, yes. I have to separate again, but sooner or later you have to write this in exponent form. So why we shouldn't do them together? It's not hard, yes. So what should I do? I write 3. What should I write for this one? X to the power of 3 over 4, then divided by 4x. Of course, you can write them separately if that's too much for you, but it's not hard. What can I do here? It's, by the way, let me write it as before, because you know that sooner or later I need to consider the coefficient in a different way, so this would be better here. Okay, this one. And the next one is minus 5 over 4, and this is the product, of course. And then x to the power of 1/2 divided by x, and then plus 1 over 4 x to the power of 2 x. Do you agree? Yes? And then simplification is also necessary. So can you tell me in your head, this 3 over 4 is 3 over 4, but can you do this calculation in your head? So you know the rule. A to the power of m divided by a to the power of n is a to the power of the exponent on top minus exponent in the bottom. Okay, so what should I do that? It becomes 3/4 minus 1. And you can do it in your head. What's the answer?
Minus 1 over 4.
Minus 1 over 4. Yes, so it becomes x to the power of minus 1 over 4. This is minus 5 over 4. What is this one now?
Minus 1.
Minus 1/2, yes. And this one?
X.
X, simplest. Now everything is in order. Now I start the process. The process, you know what to do, yes? So f of x is equal to 3/4, and this one is minus 1/4, so it becomes minus of 1 over 4. You should be able to do this in your head, but if not, you can just simply write it and do it in 2 steps. Doesn't matter. And then I have here minus 5 over 4, and then I have 1 minus 1 over 2 plus 1, x to the power of minus 1 over 2 plus 1, and then I have 1 over 4. This power is 1 actually, so it becomes 1 over 1 plus 1, x to the power 1 plus 1. Agree? Now, simplification. So how can I do that? So for example, I can cheat a little bit, multiply this 4 inside. It becomes minus 1 plus 4. It becomes 3. And this 3 cancels that 3. So forget about it. Yes? Is that understandable? So I multiply this 4 in the denominator. 4 times minus 4. You need to, I don't know what is this called in English, but you need to use these opportunities, yes? It was not a standard tool, but I realized that when I multiply this 4 here, this 4 will cancel that one, it becomes minus 1, and this becomes 4. 4 minus 1 is 3, 3 will cancel that one, so nothing is left, yes? So then I will have x to the power of 1 plus that one is 3/4. Yes? And then here, can you use the same trick? Yes, that's 2 is also good. You multiply here, it becomes minus 2 plus 4. What is that? Minus 2 plus 4 is positive 2. So it becomes 5 over 2. And x to the power of 1/2. And finally, this is plus 1 over 8, x to the power of 2. Or anyway, you can simplify these numbers as you like. Don't worry about these detailed calculations. They are simple. Is that understandable? And again, it was not trivial at all. The derivative of this function is that function. So actually, we are doing something. And now let me just draw a diagram. I know there is not much time, but I will finish everything now. But let me just tell you something. You help me to write something like that. Primitive function of f prime. What do you write in front? What is the meaning of primitive? You need, mathematics is like that. You need to refer to the rules. When I ask you, tell me primitive function of f, what do you need to write for me? You need to write a function whose derivative is f. Is that correct? That's the meaning of primitive function. Now I am asking you this question. Write something whose derivative is f prime. What's that? F, yes? But of course, plus any constant. Yes? If I ask you what is the primitive function of f double prime? F prime, yes? Because this becomes f prime plus c. So that's one point. So if I have a function, let me write it in this way. F prime is differentiation. Yes? Opposite direction is primitive function. The process of determining primitive function, I don't know, primitive function. Okay, so, and then of course, in this direction, you get exactly one answer. But in this direction, you get a main answer plus a constant in usual, okay? So in that direction, I have to add plus a constant as well. Is that also understandable? So we actually doing the opposite of differentiation, but going from a function to its derivative is unique. Okay, so it means that if I give you the graph of a function, the graph of the derivative is one graph. But if I give you the graph of a function, the graph of the primitive function is not unique. Is infinitely many graphs. Yes, because there is any constant. But they don't change that much. They are only shifting up or shifting down because a constant. It goes up or down. So that the behavior of the function is not totally different, but they are different because one of them passes through this point. The other one, this is not a very good shape. I should keep the exact shape a little bit higher, a little bit lower. I will talk about this later, okay? So this is the first lesson in primitive function. And I don't think it's hard at all. You need to solve the problems. There are some problems left. I will continue next time, next Wednesday. But then you get Friday for practice, okay? Okay, thank you for listening. So here I end this stream.